Hey, I'm Charlie Thompson. Welcome back. In this video, we'll talk about atmospheric stability, clouds and fog, and air masses. But first, we're going to talk about atmospheric stability. Atmospheric stability is an incredibly important concept because remember, if you want to make it rain, you need to lift air up. The reason we're lifting it up is to cool it, because in order to get rain, you need to have condensation. In order to get condensation, you need to cool air to dew point temperature. And in order to cool the air, it needs to rise, because as air rises, it expands and cools. So when we're talking about stability, we're talking about the tendency of an air parcel to rise, remain in place, or fall. An air parcel that's warmer than the air around it is unstable, and that air parcel will rise on its own, like a hot air balloon. An air parcel that's colder than the air around it will either stay where it's at, or it'll probably sink. So the air is stable. As the air sinks, it heats up, the relative humidity goes down, so you don't get rain. So really, all we care about is the parcel warmer than the air around it. If it's warmer, it'll rise. If it's the same temperature or colder, it's not going to rise, we don't get rain, and the atmosphere and the parcel are stable. Hot air balloons are a great example. Nobody goes cold air ballooning because they don't rise. Hot air balloons rise because they're warmer than the air around them, and therefore the air is less dense, so it rises. When we talk about rates of cooling and warming, we're going to be talking about two different categories. The first one is the unmoving atmosphere. There's two rates of cooling for this. Those are both lapse rates. So lapse rates refer to the change in temperature of the atmosphere as you go up through it. There's the normal lapse rate, which we talked about before in the context of temperature profile in the troposphere. So as you go up through the troposphere, it gets colder by 6.4 Celsius degrees per kilometer, and that's the normal lapse rate. And then there's the environmental lapse rate, which is what it actually is. All over the world, hundreds of times a day, they send up weather balloons to try to calculate out the lapse rate and determine if the atmosphere is going to be stable, in which case it won't rain, or if it's going to be unstable, in which case you could get rain. If the atmosphere is really unstable, then you could get thunderstorms, lightning, hail, possibly tornadoes. So the more unstable the atmosphere is, the more extreme the weather is. So we have the lapse rates, the normal lapse rate, the environmental lapse rate, and then we have the rates that apply to moving parcels of air. Those are the adiabatic rates. There's the dry adiabatic rate, which is that a rising parcel of air will rise and cool by 10 degrees for every kilometer it goes up, and the moist adiabatic rate, which is 6 Celsius degrees of cooling for every kilometer the air rises. So more about the adiabatic rates. Adiabatic, the word itself means a change in temperature without a loss or gain of heat. So in this case, the air is cooling because it's expanding, not because of the temperature of the air around it. Rising air cools through expansion. Sinking air warms through compression. This is the idea behind diesel engines, for example. As you compress the fuel-air mixture, it gets hot enough until it ignites all on its own, and the heat is coming just from the air being compressed. So as air sinks, it gets compressed and it heats up. As air rises, it expands and cools. So here we've got a diagram showing if we have air at 32 degrees at the surface and it gets lifted a kilometer, it'll cool 10 degrees to 22. If we lift it another kilometer, it cools to 12. If we lift it another kilometer, it cools to 2. And the opposite is true of sinking air. So as the air sinks, it gets warmer by 10 degrees to 12, warmer by 10 degrees to 22, warmer by 10 degrees to 32. So rising air expands and cools by 10 Celsius degrees for every 1,000 meters it gets lifted. This is the dry adiabatic rate. That's the rate that dry air cools by expansion. Also, sinking air heats by compression 10 degrees per 1,000 meters. Once a parcel cools to dew point temperature, water vapor starts to condense and release heat. So within a parcel, as it rises and expands, it cools by expansion, but then as water vapor condenses, it releases heat. So the moist adiabatic rate is 6 degrees of cooling for every 1,000 meters of lifting. there's 10 degrees of cooling, but then 4 degrees of heat released by the latent heat of condensation. The latent heat of condensation is one of the most important ideas in the whole chapter. The idea that as you put heat into water, it evaporates, and then that energy is in the water. When the water condenses, the energy is released, warming the air around it. Once the air, as it's rising, cools to the dew point temperature and you get condensation, that altitude is called the lifting condensation level, although often we just abbreviate it as the LCL. So lifting condensation level is the height at which condensation begins to occur. And you can see this yourself as you walk around. If you look at clouds, this is why clouds have flat bottoms. As the air is rising, it's more or less uniform in temperature and humidity. And so as it expands and cools, that's going to happen at about the same altitude, so you get flat bottoms on clouds. Once the air hits condensation, once it cools to dew point temperature, as it keeps rising, it's still going to remain at dew point temperature, so clouds are bumpy on top, but they're flat on the bottom. Here we have a diagram showing how air is going to cool as it rises, starting with 20 degrees at the surface. If we have a parcel of air that we lift up a kilometer, it's going to cool by 10 degrees. And in this example, our dew point temperature is 10 degrees. It hits 100% relative humidity. You get condensation, which releases heat. So now, once you've hit 100% relative humidity at the dew point temperature, the parcel is going to cool at the moist adiabatic rate of 6 degrees. If the rising air parcel is warmer than the air around it, it's unstable. If the air parcel is cooler or the same temperature, then it's stable and it won't rise on its own. So here we have two examples looking at a parcel of air cooling at the dry rate. And in this case, we have an environmental lapse rate of 12. So the air, the atmosphere, as you go up, every kilometer you go up, it gets colder by 12 degrees. Down to 13, 12 degrees, down to 1, 12 degrees, negative 11. Our parcel is cooling at 10 degrees, so every kilometer you go up, the parcel cools by 10, but the air around it cooled by 12. So they were the same temperature, but at 1 kilometer, the parcel is 2 degrees warmer. If we lifted another kilometer, we'd see the atmosphere that's not moving, cooling at the ELR, has cooled to 1. Our parcel is cooled to 5, so now it's 4 degrees warmer. If we lifted another kilometer, it's going to get another 2 degrees warmer, so now it's 6 degrees warmer than the air around it. You can see in this example, as we keep lifting it, it will become warmer relative to the air around it. It'll get warmer relative to the air around it. It's cooling the whole time, but it's cooling more slowly than the air around it. So it's 2 degrees warmer, it's 4 degrees warmer, it's 6 degrees warmer. As our parcel rises, it's getting more and more unstable as it gets relatively warmer than the air around it. On the other hand, if the ELR is low, for example 5 degrees, we start off again with the same temperature, 25, 25. If we lift that parcel a kilometer, our parcel cools by 10 degrees, down to 15, but the air around it, since the ELR is 5 degrees of cooling, is going to cool to 20 degrees. So now our parcel is 5 degrees colder than the air, so it's going to resist rising. It's not going to rise unless it gets lifted up by a mountain. Without a mountain, though, the atmosphere is going to be stable. The parcel is not going to rise. We're not going to get rain. In this diagram, we have a parcel of air that's rising and cooling at the dry rate up to the dew point temperature. You can see the ELR here is 8. The dry rate is 10, so the atmosphere is cooling off a steady 8 degrees per kilometer. Our parcel starts cooling off at 10 degrees, so by the time it's up to 2 kilometers, it's going to be 4 degrees colder than the air around it, so it would be stable. If, however, that air parcel now hits the condensation, the lifting condensation level, it's cooled to dew point temperature, now it's going to cool by 6 degrees, the air around it's going to cool by 8. So if that parcel, for example, gets lifted by a mountain, if it rises another 2 kilometers, now they'll both be the same temperature because our parcel started cooling by 10 for 2 kilometers and then by 6 for 2 kilometers. The atmosphere, though, has been cooling at 8 the whole time, above 4 kilometers, our parcel is going to be warmer because it's cooling by 6 degrees. The atmosphere is cooling by 8 degrees. So above 4 kilometers, our parcel is going to be unstable. And you can tell by looking at the chart, the temperature of the parcel is on the right-hand side. The right-hand side is the warmer side of the temperature profile. So above 4 kilometers, you can see the blue line is to the right of the red line. So the atmosphere is colder than our parcel. So if the parcel is warmer than the air around it, it's unstable. Clouds and fog. A cloud is just moisture droplets or ice crystals suspended in the air. If it's on the ground, we call it fog. And I've included down here a link to the National Weather Service's Jetstream site, which is one of their educational sites. You can go there and read about clouds, how they're formed, what the different clouds can tell you about the environment. I hope you check it out. You could learn some stuff and it's fun. Precipitation is just liquid or solid water, so that's rain, snow, hail falling from the clouds. Often we just call that precip for short. Clouds are made of moisture droplets. Those are made of droplets, which are even smaller droplets. Those droplets form on cloud condensation nuclei. In order for water vapor to condense, and this is really weird. It's just weird. Water vapor needs to condense out onto something. So water vapor, when it condenses, you might have seen water vapor condensing out onto a glass if you have a drink with ice cubes in it. It's condensing out onto the glass, not the air by the glass. That would be really cool. You could have a little cloud around your glass, but that doesn't usually happen. So water vapor condenses out on these things called cloud condensation nuclei. Those are microscopic particles. There's probably 1 billion in every cubic meter of air that we are used to. They're made of soot, dust, ash, pollen, smoke. All of those act as cloud condensation nuclei. So for water vapor to condense, you need to have saturated air and cloud condensation nuclei. These are some cloud words. Luke Howard is the scientist back in the 1800s that classified clouds. He was an amateur naturalist, and he thought it would be a good idea for science to classify clouds in the same way that they were beginning to classify living organisms. And his clouds have Latin root words. So if you didn't grow up speaking Latin, these words are probably new. And I think if you learn the words, it'll help you understand the clouds and remember them better. They're not just nonsense words. So the first one, cirrus. Cirrus means hair, like wispy hair. Cirrus clouds are made of ice crystals, and they have this distinctive wispy appearance. Cumulus means heap or pile. Little puffy cotton ball clouds are cumulus clouds. Stratus means layer. Alto is the prefix for 2 of the mid-level clouds, Altostratus, Altocumulus. Alto means not the highest. So the highest are Cirrus, Cirrostratus, Cirrocumulus, and then the mid-level clouds are alto something, Altocumulus, Altostratus. The word nimbus means rain, so Cumulonimbus means pile of rain. The thunderclouds are piles of rain. Nimbostratus would mean layer of rain. Harry Potter's broom was a Nimbus 2000. So Luke Howard divided clouds into 3 categories, actually 4. He had high clouds. Those are above 6,000 meters. They're made of ice crystals. They have a distinctive appearance. We'll talk about that in a minute. There's the mid-level clouds, the alto clouds, and then there's the low clouds. Those go from the surface up to about 2 kilometers. And then puffy clouds, although really it's just the cumulonimbus cloud, and those go from the surface up to 6 to 10 kilometers. So they really transcend the divisions of altitude. So we have the high clouds. Those are above 6,000 meters. They're made of ice crystals. The most important ones probably are cirrus. Those are wispy. Cirrus clouds tell us that a storm is probably coming in 24 hours. So if you see these wispy cirrus clouds, it's an indication that a storm is coming. Or rather, it can be. Cirrostratus is a layer of hair. And then cirrocumulus means little piles of hair. The mid-level clouds are alto clouds, so altocumulus means mid-level little piles. Altostratus is a flat layer. It's very boring. For the low clouds, we have stratus, flat, probably the most boring of all the clouds. Cumulus, little puffy clouds. Stratocumulus, which is a layer of little puffy clouds. Nimbostratus, if it's flat with rain coming out, it's Nimbostratus. And then the vertically developed clouds. The towering Cumulonimbus, the thunderstorm clouds, we'll talk about them in a minute. They produce lightning, they produce thunder, wind gusts. They have ice crystals and frozen water in them. They can, if they get large enough, they can develop tornadoes. And here's a good diagram of cloud types. So starting with the highest clouds, we have cirrus clouds, the wispy cirrus clouds. Cirrostratus shown here with a halo. Ice crystals refract or bend the light from the sun. So cirrostratus, cirrus, and cirrocumulus clouds, you can get this distinctive halo, and that tells you that the clouds are made of ice crystals. So we have cirrus, cirrostratus, cirrocumulus. For the alto clouds, we have Altocumulus, little puffy clouds, a layer of little puffy clouds. Altostratus, which is just a flat layer. Nimbostratus, it's a layer with rain coming out. Stratus, it's just flat. Cumulus, the little puffy clouds, I think we've all seen those. And then Cumulonimbus are the largest. They can go from just a couple hundred meters off the ground up to, like I said, 10,000 feet in the air. Let's look at some close-ups, though. We have Cirrus, the distinctive wispy ones. Altostratus, it's a boring, flat, mid-level layer. Altocumulus, they're puffy. They're not made of ice crystals, and we can tell because they look like little cumulus clouds. So they're farther up in the sky, they're higher in the sky, but they're not made of ice crystals. They're Altocumulus. Altostratus, again, the boring flat layer. Again, in this case, it's over Mount Shasta. We'll see Mount Shasta a lot. People really like taking pictures of Mount Shasta with clouds on top of her. Stratus, it's just a layer. It's boring. Nimbostratus, at least there's rain coming out of it. Cumulus, little puffy cotton ball clouds. And then Cumulonimbus. These are the largest clouds. Here is a Cumulonimbus cloud taken in flight from an airplane. And you can see Cumulonimbus clouds have this distinctive flat top. They're often called anvil clouds, like the anvils that Wile E. Coyote drops on his head. And what happens is as the air is rising, it's rising because it's warmer than the air around it until it runs into the top of the troposphere, the tropopause. And at the top of the tropopause, there's the isothermal layer where the ELR goes to 0. So the air temperature here is the same as the air temperature here. As the air rises in the cloud, though, the air in the cloud, as it rises, expands and cools. So as it rises and cools, it's colder than the air up here, so it can't rise anymore. It's like an inversion layer almost. And the other reason that the cumulonimbus clouds get flattened off is by the jet stream. So high winds in the jet stream make them flat, and they also flatten as they run into the isothermal layer at the tropopause. To make a cumulonimbus cloud, there's a positive feedback loop that has to happen. As the air rises, it expands and cools. You get condensation, which releases heat, which warms the air a little bit. So it keeps rising, and that happens again. As it rises, it expands and cools, which causes condensation, which releases a bit of heat, so it keeps rising. As it does that, it's going to pull in more warm, moist air. And that process is, like I said, like a feedback loop. The bigger it gets, the bigger it's going to get. Here's another cumulonimbus. This one's over Florida, taken, I think, from the space station. And you can see the distinctive flattening out, almost like the air has hit an invisible barrier, which it has. And that invisible barrier is probably the isothermal layer at the top of the tropopause. So cumulonimbus are thunder and lightning clouds. To make them, you need lots of warm, moist air. Remember, it's that latent heat of condensation that powers cumulonimbus clouds. As the water vapor condenses, it releases heat, which warms it and the air around it. You need a very high ELR, so as your air is rising, it's cooling more slowly than the air around it. And you need light winds to keep the storm moving along, otherwise it would run out of warm, moist air. Here is a diagram, another diagram of a cumulonimbus cloud showing the lifting condensation level, again, flat-bottomed. Here's the freezing level, so as the air rises, it's going to expand and cool. You'll get condensation. So down here, the cloud's made of water droplets. Here, it's made of ice droplets. And this is how we get hail. The air, as it rises, And the water, the rain instead of falling down, because there's these updrafts, and the updrafts can hit 125 miles an hour straight up. So as the water gets picked up, it freezes, becomes hail, and as it falls down, it'll often get picked up by another updraft, and it can make several trips around, and so the hailstones get bigger and bigger and bigger and bigger and bigger. This picture here is an example of a cumulonimbus cloud over the Senegal-Mali border. This was again taken from the space station. So you can see little convection towers, little hot towers of air as they're rising in the cloud, and then the cloud spreading out when it hits the isothermal layer. This was, at the time, the largest hailstone ever recorded. It weighed 1.75 pounds. It was 18 inches in diameter. It fell in Coffeyville, Kansas. And you can see it's got many layers. It's been cut in half so we can see them. And it looks like it's made, there's 1, 2, 3, 4, at least 5, 6, 7 trips up and down through a thunderstorm. It finally fell to the ground. This is a lenticular cloud over Mount Fuji. Lenticular clouds are, except for the fact that they're both clouds, the exact opposite of a cumulonimbus cloud. So to make a lenticular cloud, you need to have warm, moist air, a physical barrier to lift air up, in this case a mountain. You need to have a very low ELR, so the air has to be stable. As the air is rising, it expands, it cools, you get condensation which releases heat, but the air around it is still warmer. So the parcel is stable. It's not going to keep rising as soon as it runs out of mountain. The air is going to sink, heat up, the cloud's going to evaporate. And you also need winds. The winds are what is pushing the air up the mountain to make it expand and cool. So here again, I promised more Mount Shasta. Here you can see a lenticular cloud over Mount Shasta. The air is rising, expanding, cooling, and then as soon as it runs out of mountain, it sinks and evaporates. Another shot of Mount Shasta showing a different day with a different lenticular cloud. And as the day goes on, this will just hover over the mountain, although the droplets of water that come in condense and then evaporate. So really, you're not seeing a cloud, you're seeing a region of condensation that stays in place. The actual physical particles are coming and going, but the cloud stays in place, although it's not the same cloud because the water droplets keep moving. Virga, this is just a vocabulary word for rain that falls from a cloud that evaporates before it hits the ground. Fog is a cloud on the ground. In order to make fog, you need to cool warm, moist air. So there's 5 kinds of fog, and they're all classified based on what does the cooling. We've got warm, moist air. Something's going to cool it. That's what determines the 5 types of fog. So we have advection fog, evaporation fog, upslope fog, valley fog, and radiation fog. Advection fog is caused by advection. Advection is just a fancy word for wind. Air blows sideways. Our parcel of air goes over a cold surface. It gets cold and you get fog. So San Francisco's fog is caused by warm air getting blown over the cold ocean. The air gets cool. You get condensation. Bada boom, bada bing. You got advection fog. Evaporation fog happens when you have water that is slightly warmer than the air above. So this is Donner Lake, so the water is pretty cold, but the air above it is even colder. So the water evaporates, hits the cold air, condenses, and you get fog. This is swim practice fog. This would be hot tub fog, cup of cocoa fog. I can see my breath on a cold morning fog. That's evaporation fog. Upslope fog is just another way of, it's orographic lifting. The air is getting lifted because it runs into a physical barrier. It's the same process that creates lenticular clouds when the air gets moved up a mountain. That's called orographic lifting. So you've got warm, moist air. It gets lifted up. It cools. Instead of making a cloud, it's on the ground, so we call it fog. The opposite of upslope fog would be valley fog. With valley fog, you have a valley, and on the sides of the valley, it gets cold. As it gets cold, the air gets more dense, and it flows downhill into the valley where it mixes with the warm air, cools it, and makes fog. So it's a density current of the air sinking downhill because it's colder and therefore more dense than the air around it. Puddles in the valley makes fog. Here's the Grand Canyon on a foggy day. This again is valley fog, where you can really see that the fog is just down in the valleys. We get valley fog. And on this day, the thickness of the fog, it's not too thick because, scratch that. So here we have more valley fog, and it's a very thick fog belt. And you can tell it's thick because you can't see you can just barely, maybe you can see the Sutter Buttes just a little bit. On days when the fog is thinner, when it doesn't go so far off the ground, you can see just the top of the Sutter Buttes sticking out above the fog belt. And then you can see snow over the Sierra Nevada. Radiation fog is formed when the ground radiates heat and gets cold. I would call this personally cold ground fog because that's a much better term. That's what it's actually caused by. The mechanism is radiation, but people get confused with like atomic stuff. So I'm going to call it radiation fog, but in my head I think of it as cold ground fog. Doesn't occur over water. Remember, because of land-water heating differences, water cools off slowly. So over water, you're not going to get radiation fog. It's not radioactive. So heat radiates from the ground. You got to have a clear night. Can't be over water. But the ground radiates heat. The ground gets cold. You get fog. Radiation fog. The Central Valley is a wonderful place for fog. We have radiation fog, we have valley fog, and also because of all the agriculture, we also get a little bit of evaporation fog thrown in for good measure. So if you really like fog, the Central Valley is a great place to go. Precipitation, again, it's water that falls from the sky. There are two mechanisms that make rain. One of them is the collision coalescence mechanism, and that occurs in tropical clouds, clouds where the temperature is above freezing, and the Bergeron-Findyson process in clouds that are below freezing. So the collision coalescence mechanism, I think it's really straightforward. You have little droplets of water, they bump into each other to make bigger droplets. Those droplets bump into each other to make bigger droplets. Eventually you get a drop that's big enough to fall from the sky. That's the collision coalescence mechanism. That's what makes tropical rain. In colder places, like all the rain we get, it starts as snowflakes. So because the relative humidity is higher over ice than it is over water at the same temperature, water vapor is going to deposit onto the ice crystal rather than condense out onto either a condensation nuclei or an existing droplet of water. So you've got water molecules sublimating off of the ice and depositing back on the ice. You have water molecules evaporating off of the water and condensing on the water. But the overall trend is that more of the water molecules will sublimate out onto the ice crystal. So the water droplets are going to get smaller and smaller and smaller. The ice crystal gets bigger and bigger and bigger until it gets large enough to fall. In the wintertime, the air under the cloud is warm enough to melt the snowflakes, so we just get it as drops of water. We get rain. But all the rain that we get in the wintertime starts off as a snowflake in the cloud. So here's a chart showing the saturation vapor pressure, which is another way of looking at humidity. So here's a chart showing that relative humidity is higher over ice than it is over water. This also creates fall streak or hole punch clouds. So what's happening is you've got an altostratus cloud. It's right about freezing. So the droplets are going to be made of water that's close to freezing. And you've got ice crystals. So what's happening is the water vapor is evaporating, it's sublimating out onto the ice crystals, and then the ice crystals are falling from the sky. So over time, the hole is going to get bigger and bigger and bigger as the water evaporates, and then sublimates out onto the ice crystals. And those again are called hole punch clouds or fall streak clouds. Speaking of ice crystals, the humidity and the temperature determines the shape of ice crystals or snowflakes. Depending on the temperature and humidity, you can get needles or columns or flakes or plates, and all of those refract light, they bend light. They are why ice crystal clouds have this distinctive corona or halo around the sun or around the moon. This is just an amazing photo. This is a sundog. This is a sundog. The two bright spots on either side of the sun are called sundogs. And here's a chart showing you the different names for the perihelix circle, the suncave peri-arc, the upper tangent arc, the supralateral. I'm not going to quiz you on any of this stuff, but it's kind of cool that people have figured out names for them all. And this diagram is really, really close to this actual picture. Oh, including these little weird things. Man, what an amazing planet. This picture is taken, I believe, in Antarctica, and in it you can see two halos, one halo, two halo, 22 degrees away from the sun, 44 degrees away from the sun. Here we have more Virga. I believe this is in Alaska. And now we're going to talk about air masses. So with air masses, the name tells you everything. There's a system for naming them. The first letter is lowercase. It tells you how humid that air mass is. You got your two options, M for maritime, and those are air masses from the ocean, so they're moist. You could even remember that as M for moist. C for continental, those air masses are found inland. They are drier because the land is not made of water. The second letter is uppercase. The second letter tells you the temperature. We have T, capital T for tropical, those are hot. P for polar, cold, and A for Arctic. Those are super cold. Air masses are continent-sized blobs of air. I'll show you a diagram in a minute. You can see just what I'm talking about. They extend up through half the thickness of the troposphere, so up to about 6 kilometers or so. They have uniform temperature and humidity. So throughout the air mass, the temperature and the relative humidity and the specific humidity, it's all going to be about the same. When two different air masses meet, they don't mix. They form a front at the boundary layer between them. Cold fronts, warm fronts, we'll talk about that later when we talk about weather in this chapter. And here's a diagram of summer air masses. So little m, big P, maritime polar. So we'd know that it would be cool and moist. Maritime tropical. Maritime would be moist, so that would be really warm, really moist. In fact, specific humidity of 13 grams. Over here in the Gulf of Mexico, the Caribbean, the water temperature is higher, so there's more evaporation. So the air masses there are going to be more moist at 17 grams. Continental polar, 4 grams. Maritime polar, 4.4 grams. Cooler, drier. In wintertime, we can develop continental Arctic air, which is incredibly dry, 0.1 grams of water vapor per kilogram of air. In California, we deal with maritime polar and maritime tropical. If we lived in the Midwest or on the Northeast, we would be dealing with continental polar or even continental Arctic air, which would be much, much, much colder. As air masses move along, they gradually change. So when they start out, for example, that air mass over the ocean, it's going to be the temperature, it's going to be the humidity, it's going to reflect the characteristics where it started. As it moves inland, it's going to get lifted up, it's going to cool, you'll lose water vapor, so it'll get drier, and it'll gradually take on the characteristics in terms of temperature and humidity of the new location. A great example of this is called lake effect snow. So over the Great Lakes, in the wintertime, you have these very cold, very dry air masses moving over, and as they move over the Great Lakes, evaporation is occurring. So the air masses pick up water vapor, and then you get condensation and clouds, downwind from the lake. So upwind, like right here is Chicago, nothing going on there. Downwind, it looks like they're getting lots and lots and lots of snow. So if we look, for example, at Chicago, Chicago's getting 3 to 5 feet of snow in a year. And then just downstream, they're getting 60 to 100 inches of snow. My favorite example is Detroit, 2 to 3 feet of snow in a year. upwind of Lake Erie, downwind in Lake Erie, Buffalo's getting between 100 and 130 inches of snow. So they're getting 10 feet of snow. 2 to 3 feet, 10 feet of snow. The next unit is going to be on processes that lift air, and I'll cover that in the next video.